Thank you very much to the presenters and the audience for being here today. This is our third doctoral meeting session. It's a quite exciting session on again, electric propulsion for space environment. And we'll be having today 7 presentations by Maria Sherezade, Celia Amboyé, David García La Huerta, David Madaloni, Víctor Gómez García, David García Villegas, and Borja de Saavedra. Basically, we're going to be today listening to 3 presentations on the Zarathustra Starting Ground project that Mario presented to us in March, and you have the presentation and the recording should you want to check what he's proposing. So it will be a good opportunity to listen to his project. Maria will be presenting her thesis on Micropulse plasma thruster design. So again, an experimental PhD thesis, very interesting one. And then we'll be hearing to 3 industrial PhDs with CENER and ENI Space. ENI Space indeed is a spin-off of some research that was done in EP2 group 2-3 years ago. So it's very interesting also to see what we are being able to transfer to society in the form of a spin-off and new positions for people and groundbreaking research. As you know, the presentation should be 10 to maximum 15 minutes long, right? So keep an eye on the time. We will be strict on the time, right? Because then we'll need some minutes for questions. Needless to say, I think I can give the ball to Maria Sherezade for her presentation. So go ahead, Maria.
So good morning, everyone. Thank you. Okay. So this thesis concerns the numerical and experimental work around an ablative pulsed plasma thruster for space micropropulsion. And this device is commonly known by its initial APPT. So this is what I'm going to use. And ablative is because of the use of a solid state propellant. So as a summary of the content after the introduction of the project that motivates this research and the justification of the choice of this technology, I'm going to introduce the high-level objectives of my thesis and a brief presentation of the experimental advances that we have done up to this moment, together with the enumeration of the next steps in the short time. So firstly, this work is framed by the Martin Lara project, that this is a regional project, and within its context, apart from the development of the mission and the nanosatellite itself, different scientific challenges have to be addressed to be finally airborne validated. And one of these challenges is the development of a micropropulsion module made on electric propulsion, and this was won by EP2 challenge, and this is my work. So hence the fundamental requirements to start this work are based on to provide a specific impulse in the order of 1000 seconds and an impulse speed in the order of tens of micronewtons per seconds, and a device that can be suitable to be scaled down and ensuring obviously robustness and reliability, and with a power consumption consistent with the usual power budgets for micropropulsion for CubeSat standards. So, sorry. Well, so why did we choose APPT for this purpose? Let's start by the explanation of its working principle. We have 2 electrodes that extend axially, defining an acceleration channel, and they are spaced by an insulator that is the propellant. This kind of devices work with a plasma discharge that happens between these 2 electrodes. And once this impedance collapse happens, the gap between these electrodes that joins them with an energy source that was previously charged is closed. So high current develops, also a magnetic self-magnetic field, and the interaction between these 2 magnitudes provoke body force and accelerating body force that that makes this plasma to be expelled down the channel. So summarizing the advantages of these, sorry, because these are videos, but I cannot, yeah, sorry. So these are mainly the advantages of using this kind of technology for micropropulsion. The easiness for scalability in terms of structure, power, budgets, and electronics in comparison with other electric propulsion thrusters. Because if it's simplicity and the absence of injection system in the case of solid propellant ones. So even though that unsteady operation is difficult in terms of modeling and experimental diagnostics, it has some modern advantages as the less erosion in terms of the main electrodes, and also a power budget that is assumable for CubeSats. So also just varying the number of firings and the frequency of the firings, we can take advantage of a variable average thruster. So however, as I said, the unsteady regime is something difficult, and we have to be careful designing PCB based on high voltage, high currents, and pulse generation. Considering also that this kind of devices works with waveforms that are under the impede, and also they involve reversal of currents, the regime that we are interested in. So the mechanisms that are behind this plasma formation and generation and acceleration, sorry, are complex, and contrast with this simplicity that I mentioned about the structure. However, these difficulties, sorry, I'm so nervous. In this slide, I'm showing a series of examples of the data that we were collected during these months. This kind of ignition in vacuum is not straightforward at all, as we want a discharge that develops around the surface of the propellant. Even though this is supposed to be the weakest path to develop a plasma discharge, this gap, the order of magnitude of the gaps that we are managing, that is 1 centimeter, involves extremely high voltage that are not assumable for our PCBs, or at least we don't want to be in that regime. So we need an additional triggering method that usually is a kind of another APPT in a small scale. That this is the configuration that we are usually using, and the characteristic length of this triggering is about 1 millimeter, and with it we can manage these charges under 10 kilovolts. So, sorry. Also in these frames, the quality of the images are not so good because they are taken with a normal camera, but we are going to use a fast camera and also filters in the next weeks in order to provide more information about the plasma distribution and the species. And along the experiments, we also saw that there are different regimes for example, from diffusive plasma paths up to very concentrated paths that are visible from the nude site, and other non-uniform phenomena. For example, the inclination of that concentration region or attachment points. So I've done an exhaustive experimental literature review of existing PPTs and other fields with which to establish analogies with. And 3 main objectives have been defined for this thesis that are based on numerical modeling and coding, that this is a work in progress at this moment, and the design, development, and preliminary testing of a breadboard model that I was doing during the last year approximately, with the final aim of providing a final, complete, and compact engineering model that fits with the requirements of the project. So going now deeper into the simulation objective, the models used usually are electrical, even though they are simple, so this is an advantage. Even though that they fit with the overall performance, they are not enough to deal with the low efficiency reported up to this moment, because they do not consider the plasma nature itself. So we are developing to the unsteady magnetohydrodynamic approach to save this to face this absence. We are addressing the problem with the methods of the characteristics, and it constitutes an open work. So going now into the experimental characterization in detail, the main focus that was the main focus of this last year. The main objectives based on the better understanding of the physics and to provide an experimental database in order to validate future simulation models, and also with the aim of prototype optimization, for example, of the electromagnetic component, the electronics, the triggering method, or and finally the predictability of and the repeatability of the discharge itself. So a comprehensive report about the system requirements was done, but as an intermediate necessary step to face these the former objectives, it was necessary to develop a breadboard model that enables us to explore different geometries and electronics, allowing fast iteration according to the changing experimental needs. So after multiple iteration, this was our model, but now we are working with a simplified version because we have faced a lot of difficulties in the last months regarding ignition and also measuring, and in order to be able to remove the influence factors as far as possible, we decided to simplify it a lot. So regarding the data collected in this ongoing preliminary campaign, we can differentiate two objectives, and we are now in the first part that deals with the learning about the necessities, the difficulties, and the characteristics of the vacuum ignition, the triggering circuit, and the high frequency and high voltage electronic measuring, and also the coupling between the both discharges, the triggering one and the main channel one. So in function, sorry, of main parameters, geometrical and electronics ones, as the voltage of the configuration of the ignition system and the electrode voltage, the energy area ratio, the gap, or the role of the propellant itself. So this figure represents the main channel discharge, but also we can have an analogous form for the spark plug waveforms. We have to explain correctly the singularities that we often find, and also to determine which is the best operational regime and configuration. So in order to find that reliable operational point and configuration, we are doing a series of preliminary tests, as I said. And also, once we have it, what we want to do is a detailed parametric study to provide a complete time and space characterization of the plasma, including the species that conform that plasma, to finally identify the causes behind the non-uniform phenomena and the efficiency losses. So finally, to recap, a list of planet diagnostics is presented. Some of them have been already done, or I'm working on them, and other are not being prepared, still prepared, and are planned for the next months. The current work is based on the electrical characterization principally, and the overall the determination of the overall appearance of the discharge. It have been facing during these months the difficulties concerning the, as I said, the to work with high frequency, current, and high voltage waveforms that affect the probe definition, the procurement of the equipment, the to do the experiment itself, and after that to interpret the results. So this time planning can be just approximated, and it will depend on the the work of the next months and the difficulties that we are facing the day by day. So as a consequence of this, for example, we were developing during the previous year through a bachelor thesis and the design of an impulsive torsional thrust balance on purpose for this APPT. But finally, it has been postponed until the moment that we have more advanced breadboard models. So to conclude with the dissemination works, apart from the reports and presentations concerning the internal meetings for the Martin Lara project, I participated in one conference with an oral presentation and the corresponding paper that you can find here, and about the design itself of the breadboard model. I was accepted to participate in the MPCS conference of this year, that we are planned to show the preliminary results, experimental results, and maybe a study of the ignition, the triggering method, that as we tried many configurations and we were collecting numerous data concerning this. Also, as I mentioned, under the frame of this thesis, bachelor thesis was being guided concerning the design of the thrust balance, and also it participated on as a challenge, a student challenge in the NanoStar project, and also the design of this breadboard model was one of the student challenges. And this is a representation of the cut of that thrust balance. So thank you so much, and if you have any question.